Well, I've claimed now that the law of quadratic reciprocity is really an amazing way to compute Legendre symbols, so let's actually see why that's the case. First up, we've computed the Legendre symbol 7 by 31 twice already, but let's do it again. 7 and 31 are both odd, and they're both primes, and they're not the same number, so let's apply the law of quadratic reciprocity. Check the values of the primes mod 4. 7 and 31 are both equivalent to 3 modulo 4. So if both primes are equivalent to 3 mod 4, the two Legendre symbols are opposites of one another. So instead of computing the Legendre symbol 7 by 31, we're going to compute the Legendre symbol 31 by 7, and then multiply that by -1. Now 31 by 7 asks, is 31 a quadratic residue modulo 7? But if we're working modulo 7, 31 is not really what we have to work with. We can replace 31 with 3. 31 and 3 are equivalent modulo 7. So 31 is a quadratic residue mod 7 exactly when 3 is a quadratic residue mod 7. So instead of computing the Legendre symbol 31 by 7, let's just go with 3 by 7. Notice these are both odd primes and different from each other. They're both equivalent to 3 mod 4. So the Legendre symbol 3 by 7 is negative Legendre symbol 7 by 3. 7 is larger than 3. So if I'm asking, is 7 a quadratic residue modulo 3, I can just as well ask, is 1 a quadratic residue mod 3? And 1 is definitely a quadratic residue mod 3. It's 1 squared. So the Legendre symbol 1 by 3 is equal to 1, because 1 is definitely a quadratic residue modulo 3. The Legendre symbol 1 by 3 is equal to the Legendre symbol 7 by 3, which is the opposite of the Legendre symbol 3 by 7, which was equal to 31 by 7, which is the opposite of 7 by 31. Altogether, 7 by 31 is negative 31 by 7, so that's negative 3 by 7, which is now positive 7 by 3, which is 1 by 3, which is 1. So overall, 7 is a quadratic residue modulo 31, which matches what we've already seen twice before. But let's look at more examples. Determine whether 30 is a quadratic residue modulo 101 or not. You could do this with Gauss's method. It would require listing out 50 consecutive multiples of 30, and in fact, we did do it as an example of Gauss's method. But listing out 50 multiples takes some time. 30 is not a prime, however, so you might think quadratic reciprocity doesn't apply. But the Legendre symbol is multiplicative, and 30 is 2 times 3 times 5. So instead of doing the Legendre symbol 30 by 101, let's just do each of 2, 3, and 5 by 101, and then take the product. The last two terms do now involve two distinct odd numbers, 3 and 101, or 5 and 101. So those last two terms I can apply quadratic reciprocity. Since 101 is equivalent to 1 mod 4, the Legendre symbol 3 by 101 is equal to the Legendre symbol 101 by 3, and similarly for 5. However, 101 can be reduced mod 3 and mod 5 respectively. So asking if 101 is a quadratic residue modulo 3 is the same question as asking if 2 is, because 101 is equivalent to 2 modulo 3. Asking if 101 is a quadratic residue modulo 5 is exactly the same question as asking if 1 is, because 101 is equivalent to 1 modulo 5. We can't use quadratic reciprocity on the first term up here, nor can we use it on this term, because 2 is not an odd prime. Common mistake is to try to apply quadratic reciprocity again. But remember, quadratic reciprocity requires both arguments to be odd primes, and 2, for all of its interesting properties, it's not odd. Okay. However, we have established that the Legendre symbol 2 by p is 1 if and only if p is equivalent to plus or minus 1 mod 8. We did this using Gauss's method. So 2 by 101 and 2 by 3, I can exactly attack by asking the primes 101 and 3, what are they equivalent to modulo 8? Well, modulo 8, 101 is equivalent to 5, and 3 is equivalent to 3. So the Legendre symbol 2 by 101 is -1, because 101 is equivalent to 5 modulo 8. The Legendre symbol 3 by 101 we determined is equal to the Legendre symbol 2 by 3. Now that I have 2 over a prime, I ask, what's this prime equivalent to mod 8? Was it plus or minus 1? No, it was not. Therefore, this Legendre symbol is also minus 1. And here I have the Legendre symbol for 1. Is 1 a quadratic residue mod 5? Of course it is, so that takes value 1. Overall, -1, -1, 1, the product is 1. So quadratic reciprocity has shown us that 30 is a quadratic residue modulo 101. So what did we really go through in the previous example? The Legendre symbol is only defined when P is an odd prime, so never stick a 2 in the bottom argument there. If P is a factor of A, or if A is equivalent to 1 modulo P, we can immediately say the Legendre symbol is 0 or it's 1. Otherwise, A is equivalent to some value between 2 and P minus 1. That top argument, since we're talking about things modulo P, can be reduced modulo P. So it's either 0 or 1 or something between 2 and P minus 1. But then A, if it's something between 2 and P minus 1, can be factored into a product of primes, all of which are smaller than P. Using the multiplicativity of the Legendre symbol, once you've factored A and split it up into the various things of primes over P, either those primes are 2, or they are odd primes that are smaller than P. We have a formula for computing the Legendre symbol 2 over P, and if Q is another odd prime, we can use quadratic reciprocity. Instead of looking at the Legendre symbol Q over P, we'll be looking at the Legendre symbol P over Q, possibly with an extra -1 thrown in there, if both primes were equivalent to 3 mod 4. So when you get a 0 or a 1 up top, easy. When you get a 2 up top, we have this nice formula here. When you have anything else, you split it up into the product of primes, and now you have other odd primes over P. But since Q is smaller than P, P is larger than Q, so you can then reduce this number modulo Q and have a different Legendre symbol where that number up top has gotten smaller, and you are talking about modulo Q, a smaller prime. So quadratic reciprocity allows you to repeat this process over and over again. Sometimes you get things that are very easy. Otherwise, you're working with smaller numbers and smaller primes until they become easy, and then you're done. So let's take a look at another example to sort of illustrate what we mean here. Compute the value of the Legendre symbol 425 by 1741. 1741 is prime. 425 definitely isn't, because it's divisible by 5. In fact, if you factorize it, you easily factor out that 5, leaving behind 85, and 85 is 5 times 17. So we have 5 squared times 17. So I'm going to split up the Legendre symbol as 25 and 17. Now, why did I do 25 rather than 2 different things of 5? Because 25 is obviously a quadratic residue. It's 5 squared. So the Legendre symbol 25 by 1741, I don't need any quadratic reciprocity or anything. I just say 25 is definitely a quadratic residue, so that first term is 1. So overall, 425 over 1741 is going to be equal to 17 over 1741. Now I have 2 distinct odd primes, and one of them is equivalent to 1 modulo 4. Actually, they both are, but it doesn't really matter as long as one of them is. 17 by 1741 is the same thing as 1741 by 17. Now I have a much larger number over 17, so reduce it modulo 17. 1741 is equivalent to 7 mod 17. So you can replace the Legendre symbol 17 by 1741 with 7 by 17, a much simpler question. Those are both odd prime numbers, and 17 is still equivalent to 1 mod 4. So the Legendre symbol 7 by 17 is the same as 17 by 7. 17 can be reduced modulo 7 to be equivalent to 3. Now I have 2 distinct odd primes, but they're both equivalent to 3 mod 4. So 3 by 7 is negative 7 by 3. 7 is bigger than 3, so reduce it. 7 is equivalent to 1 mod 3. Now I have a Legendre symbol with a 1 up top. That's equal to 1. So overall, the Legendre symbol 425 over 1741 was this. This first term is 1, so I just have to focus on this one. This Legendre symbol by quadratic reciprocity, since one of the primes was equivalent to 1 mod 4, I can just flip it and reduce this mod 17. So now I have this is overall equal to that. These are 2 distinct odd primes. one of which is equivalent to 1 mod 4, so by quadratic reciprocity, just flip it and then reduce the top one mod the bottom. Now I have two distinct odd primes, but they're both equivalent to 3 mod 4, so I can flip it, but I get an extra -1. Reduce 7 mod 3 to get something very easy, and ultimately, overall, -1. So is 425 a quadratic residue modulo 1741? No, it isn't. Now, if this is the first or second time you've seen this, this looks fairly complicated, but observe what we didn't have to do. If I applied Euler's method, what would I have had to compute? I would have had to compute 425 to the 1741 minus 1 over 2 and reduce that modulo 1741. In other words, I would have had to have computed 425 to the 800 and, let's see, 1790 over 2 is 895. Man, I don't want to do that. Terrible. What would Gauss's method have us do? I would list out 425 times 2, all the way until 425 times 895, and then I'd have to take the remainders. While that's actually a lot less work than doing that enormous exponent, that's still awfully tedious. You're never going to do this by hand using Gauss's method on an exam without taking tons and tons of time. So once you get your brain around the law of quadratic reciprocity, these examples are actually very quick. All right, so more examples along these lines. Let's compute whether 620 is or is not a quadratic residue mod 3217, and you're given that 3217 is prime. Well, factor 620 as follows and split it up accordingly. Now, term by term, 4 is definitely a quadratic residue mod anything because it's 2 squared. Now, here I have odd primes that are different from one another. So I can apply quadratic reciprocity to each of these terms. Since this prime is equivalent to 1 mod 4, both of them are going to just be flipped for free. So this is definitely a quadratic residue, so I get a 1. Quadratic reciprocity allows me to flip this and allows me to flip this. Since each of them had a prime that was 1 mod 4, I don't have to introduce extra -1s. But now this term is asking about something mod 5, and this is asking about something mod 31. So simply reduce that large top number, modulo 5 and 31 respectively. 3217 is equivalent to 2 mod 5, and it's equivalent to 24 mod 31. So here I have 1 prime with respect to another, but 2 is not an odd prime. So I apply that other question, what about the other one? Is it equivalent to plus or minus 1 mod 8? No, 5 is not equivalent to either 1 or -1 mod 8. So 2 is not a quadratic residue mod 5. So this first term is a -1. Then I can turn my attention to the Legendre symbol 24 over 31 by factoring 24. So I get a minus term from this one. Then I factor 24. Well, on the one hand, it's 8 times 3, but 8 is 4 times 2. And why would I split it up like this? Well, 4 is definitely a quadratic residue mod 31 because it's 2 squared. Here I have a 2, so I apply that same question. Is 31 plus or minus 1 modulo 8? Yes, it is. It's -1 mod 8. So 2 is a quadratic residue mod 31. Then in the last term, I'm just going to have 2 distinct odd primes. So here I get a 1. Here I also get a 1. I'm still got this minus sign carried from previous terms. But now I have 3 and 31 that are both equivalent to 3 modulo 4. So I can apply quadratic reciprocity, but I have to introduce another minus sign, which will actually cancel this one. So overall, 620 by 3217, this minus sign is canceled. This was 1, this was 1, and I flip that by quadratic reciprocity. 31 by 3, I can now reduce this modulo 3 and get 1 mod 3. So ultimately, the question of, is 620 a quadratic residue modulo 3217 has simply become, is 1 a quadratic residue mod 3? Yes, it definitely is. Hopefully we're convinced that the law of quadratic reciprocity is a really nice way to compute Legendre symbols. But now we're going to attack a more abstract problem. We're not going to try to compute one specific Legendre symbol, but something more general. For which primes p is 3 a quadratic residue? In other words, for which odd primes p will the Legendre symbol evaluate to 1? If p is 2, I can't put it as the bottom argument for a Legendre symbol, but I can simply say 3 is equivalent to 1 mod 2, and that's definitely 1 squared. So 3 is a quadratic residue modulo 2. Otherwise, let's talk about odd primes. Well, if p is 3, the Legendre symbol 3 over 3 is 0, because 3 is a factor of 3. So now, let's just suppose p isn't just an odd prime, but it's also bigger than 3. Now that I have the Legendre symbol 3 over p, where p is an odd prime and it's bigger than 3, I can apply quadratic reciprocity. 3 is equivalent to 3 mod 4. So when I flip this using quadratic reciprocity, I need to ask, do I have to introduce an extra minus 1 or not? That depends whether both primes are equivalent to 3 mod 4 or not. So in fact, I need to ask, is p equivalent to 1 mod 4 or is it not? But we have just a general odd prime. So we're going to have to do this by cases. We have, however, this. I can flip it for free if p is equivalent to 1 mod 4, but when I flip it, I have to introduce an extra factor of minus 1 if p is equivalent to 3 mod 4. Because 3 is definitely equivalent to 3 mod 4, the question of whether both are just boils down to whether p is equivalent to 3 mod 4. Now, p is an odd prime larger than 3, so the value of the Legendre symbol, p over 3, is either 1 over 3, because p might be equivalent to 1 mod 3, and the Legendre symbol 1 over 3 is definitely 1, or p might be equivalent to 2 mod 3, in which case the value of the Legendre symbol is minus 1, because here I have a 2 and a prime not equivalent to plus or minus 1 mod 8. So if p is equivalent to 1 mod 3, this Legendre symbol will be 1. If p is equivalent to 2 mod 3, this Legendre symbol will be negative 1. So we have two distinct questions to ask. What is p equivalent to modulo 4? And then, what is p equivalent to modulo 3? So altogether, what do we have at this point? We know that the Legendre symbol 3 by p, when p is an odd prime larger than 3, can be flipped for free if p is equivalent to 1 mod 4, and can be flipped with an extra negative sign if p is equivalent to 3 mod 4. But then we know this Legendre symbol p by 3 is either 1 if p is equivalent to 1 mod 3, or negative 1 if it's equivalent to 2 mod 3. It's definitely not, by the way, equivalent to 0 mod 3, since it's a distinct prime from 3 and it's larger than 3. So altogether, suppose, for example, p is equivalent to 1 mod 4 and equivalent to 1 mod 3. Then you flip it and get out a 1. If p is equivalent to 3 mod 4 and equivalent to 2 mod 3, get a minus 1 and then a minus 1. Altogether, you have a 1. If p is equivalent to 1 mod 4 and 2 mod 3, flip it and get out a minus 1. If you're equivalent to 3 mod 4 and 1 mod 3, flip it with a factor of minus 1 and then get out a 1. So these are the 4 distinct possibilities based on which of these choices are made and which of these. But we can apply the Chinese remainder theorem. Each one of these lines is a statement mod 4 and a statement mod 3. 4 and 3 are relatively prime to one another, so in each line we can apply the Chinese remainder theorem. 1 mod 4 and 1 mod 3 is the same as 1 mod 12. 3 mod 4 and 2 mod 3 is the same thing as 11 mod 12 or negative 1 mod 12. So the only way we get out a 1 is by being equivalent to plus or minus 1 mod 12. The other possibilities correspond to plus or minus 5 mod 12. So the original problem was, for which primes is 3 a quadratic residue? And we've determined it boils down to asking, what is p equivalent to modulo 12? An interesting little result. And you can keep doing arguments like this, by the way, for which primes is 5 a quadratic residue, for which primes is 6 a quadratic residue, for which primes is 7 a quadratic residue, and so forth.